Hello, in this lecture we will find the radius of the small circle. In the drawing we have a square. We know that one side of a square, side AB equals to side AC equals to side DC equals to side AD equals to 8 units. And inside the square we have two circles, and we know that the radius of this big circle equals to 2r, and we also know that the radius of this small circle equals to r, and we want to find out the value of r, the radius of this small circle. Okay, so first of all I will present to you two new rules. Rule number one: states that a tangent to a circle is perpendicular to the radius drawn to its point of tangency. And read rule number one again. Rule number one states that a tangent to a circle is perpendicular to the radius drawn to the point of tangency. So actually, if we have a circle and the center of this circle is at point O, this point O, and we have also a radius, we have a tangent AB is tangent to this circle at this point M. So if we draw a radius of this circle from point O that is drawn to the point of tangency, that is to say point M. Then the tangent AB will be perpendicular to this radius, that is to say this angle equals to 90 degrees and this angle also equals to 90 degrees. Okay, so whenever we draw a radius that is drawn to the point of tangency, that is so to say the point of tangency here is point M, so whenever we draw a radius that is drawn to the point of tangency like in this drawing, then the tangent AB will be perpendicular to this radius, that is to say this angle is 90 degrees and this angle is 90 degrees. Okay, so again I will read rule number 1. A tangent to a circle is perpendicular to the radius drawn to the point of tangency. Again, whenever we draw a radius that is drawn to the point of tangency, like in this drawing, this radius is drawn to the point M, that is the point of tangency, then the tangent AB will be perpendicular to this radius, that is to say this angle is 90 degrees and this angle is also equal to 90 degrees. Okay, so actually that is rule number 1, and we also have rule number 2. Actually, rule number 2 states that if from one external point two tangents are drawn to a circle, then they have equal lengths. I will read rule number 2 again. Rule number 2 states that if from one external point two tangents are drawn to a circle, then they have equal lengths. So what is the meaning of rule number 2? The meaning of rule number 2 is that if we actually have a circle and actually this point P is an external point in relation to this circle because of the fact that point P is not located inside the circle and it is not located on the circle, Therefore, point P is an external point in relation to this circle, and if from point P we draw two tangents to this circle, and if we define the touching point between this tangent to the circle as point A, and we will also draw also the second tangent to this circle, and we will define the touching point of the second tangent to the circle as point B. So according to rule number 2, the lengths of those two tangents are equal to each other. That is to say, PA equals to PB. So again, PA equals to PB. So whenever we draw from an external point of a circle two tangents to a circle, to that circle, then the lengths of those two tangents will be equal to each other. That is to say, PA equals to PB. Okay? And again, if from one external point two tangents are drawn to a circle, then they have equal lengths. If we draw from external point of a circle two tangents to that circle, then the length of those two tangents are equal. They are equal to each other. That is to say, in this case, PA equals to PB. The length of the first tangent is PA. The length of the second tangent is PB, and PA equals to PB. Okay? So we will define the touching point. We will define the center of the small circle. This point is point P, and we will define the center of the big circle, this point, as point Q. And then we will join together points A and P by a straight line. We will define the touching point between tangent AB to the small circle as point M. Then we will join together points P and M by a straight line. Actually, line segment PM is the radius of the small circle. I will mark it as R, that is the radius of this small circle, because of the fact that line segment PM is exit from the center of the circle that is to say point P, and ends at point M, that is as a point on the circle itself. Therefore, actually, line segment PM is the radius of this circle, and we have rule number 1 that says that if a radius is drawn to the point of tangency, like in this case, we have this radius that is drawn to the point of tangency, that is to say point M. Therefore, the tangent AB is perpendicular to this radius, that is to say this angle equals to 90 degrees, and this angle also equals to 90 degrees. Okay, and we will define the touching point between we will define first of all this point as point E, and we will define the touching point between tangent AE to the small circle as point L. Then we will join together points P and L by a straight line. Actually, PL is the radius of this small circle because of the fact that line segment PL starts from the center of the circle, that is to say point P, and ends at point L, that is a point on the circle itself. Therefore, PL is the radius of this small circle, so it equals to R. And again, we have rule number 1. According to rule number 1, if a radius is drawn to the point of tangency, then the tangent is perpendicular to this radius. So here we have radius PL that is drawn to the point of tangency, that is to say point L. Therefore, the tangent AE is perpendicular to this radius, that is to say this angle equals to 90 degrees, and this angle also equals to 90 degrees. Okay, so in the next step we will prove that those two right triangles can go into each other. Those two right triangles can go into each other. So actually we will prove that the right triangle AMP can point to the right triangle APL. Okay, I will repeat again. We will prove that the right triangle AMP is congruent to the right triangle APL. Okay, so first of all, we know that side AM equals to side AL, AM equals to AL according to rule number 2. Again, AM equals to AL according to rule number 2. And actually, A is the external point to in relation to this small circle, and from point A we have two tangents to this small circle, tangent AM and tangent AL, and according to rule number 2, whenever you draw from an external point of a circle two tangent to that circle, then the length of those two tangents will be equal to each other. That is to say AM equals to AL. So again, AM equals to AL according to rule number 2, and PM equals to PL equals to the radius of this small circle. PM equals to PL equals to the radius of this small circle, and side AP is a common side, it belongs to both triangles, so AP equals to AP is a common side that belongs to both triangles. AP equals to AP is a common side that belongs to both triangles. Okay, so we actually proved that all three sides of the right triangle AMP are correspondingly equal to all the three sides of the right triangle APL. Therefore, we proved that the right triangle AMP is congruent to the right triangle APL according to side rule. So I write it down. We actually proved that the right triangle AMP is congruent. This is the sign of congruent to the right triangle APL, according to side rule. Okay. So what is side rule? Side rule is that if you prove that all three sides of one triangle are correspondingly equal to all three sides of another triangle, then you actually prove that those two triangles can go into each other according to side rule. Okay? So from the fact that those two triangles can go into each other, we will conclude that those two angles are equal to each other according to the rule that corresponding angles in congruent triangles are equal to each other. Those two triangles can go into each other, therefore those two corresponding angles will be equal to each other. So angle PAM, this angle is equal to angle PAL angle PAM equals to angle PAL according to the rule. The corresponding angles in congruent triangles are equal to each other. Those two triangles can go into each other, therefore those two corresponding angles will be equal to each other. And if we define this angle as alpha, then this angle also will be equal to alpha. Okay, because of the fact that those two angles are equal to each other. So angle PAM equals to angle PAL, and both angles are equal to alpha according to our definition. Okay, so in the next step we will join together points A and Q by a straight line. And we will define the touching point between tangent AE to the big circle, this point as point S, and we will join together points S, Q and S by straight line. Actually, line segment QS is the radius of this big circle. It equals to 2r because of the fact that line segment QS starts from point Q, that is the center of this big circle, and ends at point S, that is a point on this big circle itself. Therefore QS equals to 2r, it is the radius of this big circle. And according to rule number 1, whenever the radius is drawn to the point of tangency, that is to say point S is the point of tangency here, and we have this radius that is drawn to the point of tangency, therefore the tangent AE is perpendicular to this radius, that is to say this angle equals to 90 degrees, and this angle also equals to 90 degrees. And the same thing, first of all, we will define the touching point between tangent DA to the big circle as point E. And again, we have this radius that is drawn to the point of tangency, that is to say point E. Therefore, the tangent DA is perpendicular to this radius, that is to say this angle equals to 90 degrees, and this angle also equals to 90 degrees. Okay. So in the next step we will prove that those two right triangles can go into each other. Those two right triangles can go into each other. So actually we will prove that the right triangle AQS is congruent to the right triangle EQA. Okay. Again, we will prove that the right triangle AQS is congruent to the right triangle AQE. This right triangle. I will repeat again. We will prove that the right triangle AQS can go into the right triangle AQE. So, first of all, we know that side AS equals to side AE. AS equals to AE according to rule number 2. AS equals to AE according to rule number 2. Okay, and we have here A is the external point in relation to the big circle because it doesn't located inside the big circle and no on this big circle itself, therefore it is external point in relation to the big circle, and from point A we have two triangles, two tangents that is drawn to this big circle, tangent AS and tangent AE, and according to rule number 2, whenever you draw two tangents from an external point of a circle, then they will be equal to each other. That is to say, AS equals to AE according to rule number 2. And we also know that QS equals to QE equals to the radius of the circle. QS equals to QE equals to the radius of the big circle, that is actually 2R. Okay, QS equals to QE equals to 2R. And we also AQ or QA is a common side, it belongs to both triangles, so QA equals to QA. It's a common side that belongs to both triangles. Again, QA equals to QA is common side that belongs to both triangles, so we actually proved that all three sides of the right triangle AQS are correspondingly equal to all the three sides of the right triangle AQA. Therefore, we proved that those two right triangles can go into each other according to side rule. So I will write it down. We actually proved that triangle AQS is congruent. Again, this is the sign of congruent to triangle AQF. According to side rule. Okay. And from the fact that those two right triangles can go into each other, we will conclude that angle QAS, this angle, is equal to angle EAQ. This angle, according to the rule that corresponding angles in congruent triangles are equal to each other. So actually angle QAS is equal to angle QAE, this angle, according to the rule that corresponding angles in congruent triangles are equal to each other. Those two triangles can go into each other, therefore those two corresponding angles will be equal to each other. Okay, and if we define this angle as beta, then this angle will be also equal to beta because of the fact that those two angles are equal to each other. So we actually found out that angle QAS equals to angle QAS equals to angle QAE, and both angles are equal to beta according to our definition. Okay. Actually, we will define the touching point between tangent CB to the small circle, this point, as point N, and again we have also rule number 1 that says that if a radius is drawn to the point of tangency, that is to say point N, then the tangent BC will be perpendicular to this radius. So radius PN is on to the point of tangency, that is to say point N. Therefore, the tangent BC is perpendicular to this radius. That is to say, this angle equals to 90 degrees, and this angle also equals to 90 degrees. Okay? And we also know that all the angles of a square are right angles, so therefore angle ABC, this angle, that is one of out of four angles of square ABCD, is equal to 90 degrees. That is to say, it is a right angle. So angle ABC equals to 90 degrees. So actually we will focus on quadrilateral PNMB. This quadrilateral PNMB. So in quadrilateral PNMB, we have three right angles, 1, 2, and 3. And the sum of three right angles is 90 degrees times 3 is 270 degrees. And we know that we have a rule that the sum of the angles in any quadrilateral equals to 360 degrees. So actually the sum of these three angles, that is actually 270 degrees, plus the size of the fourth angle that we will define as angle Z, must be equal to 360 degrees according to the rule that I mentioned. Again, 270 degrees plus the size of the fourth angle that is defined as Z must be equal to 360 degrees. So here we will subtract from this equality 270 degrees, and we will get that angle Z equals to 360 degrees minus 270 degrees is 90 degrees. Okay? So we found out that this angle is a right angle, it equals to 90 degrees. Okay? So this angle is a right angle that equals to 90 degrees. And so, as you can see from the drawing, quadrilateral PNMB, this quadrilateral has four right angles, 1, 2, 3, and 4. And any quadrilateral that has four right angles is defined at least as rectangle. If not a square, it is at least a rectangle. So actually I will write it down that quadrilateral PNMB is at least a rectangle. Okay, Again, this quadrilateral PNMB is at least a rectangle, if not a square, is at least a rectangle. And we have the rule that states that opposite sides of any rectangle, the opposite sides of any rectangle are equal to each other. So, therefore, actually, the rectangle PNMB, in rectangle PNMB, we have two opposite sides that are equal to each other. That is to say, Pn equals to MB. Pn equals to MB, according to the rule that opposite sides of a rectangle are equal to each other. But we know that Pn equals to R. Pn equals to R. So, from this equality, we will conclude that MB also equals to R. MB also equals to R. So MB equals to R. And according to the rule that opposite sides of a rectangle are equal to each other, in rectangle PNMB we have side PM that equals to side NB. PM equals to NB. But we know that PM equals to R. PM equals to R, and again, from this equality, we will conclude that NB also equals to R. NB also equals to R. Okay, so we actually found out that quadrilateral PNMB has 4 right angles and also 4 equal sides. Both of all its sides are equal to each other, and they are equal to R. Therefore, actually, quadrilateral PNMB is a square. Okay, quadrilateral PNMB is a square, and in the next step we will calculate the size of AM. The size of AM, actually, as you can see from the drawing, AM equals to AB minus MB. Again, AB minus MB equals to AM. I write it down. So AM, this side AM or line segment AM equals to AB, that is the size of one side of triangle ABCD. It equals to AB minus MB. AB minus MB equals to AM. So AM equals to AB, AB equals to 8 units. Here we know that AB equals to 8 units. AB equals to 8 units. And MB equals to R. Okay? So AM equals to AB minus MB, and AB equals to 8, and MB equals to R. So in total, AM equals to 8 minus R. So we found out that AM equals to 8 minus R. Again, AM equals to 8 minus R in the, so actually we know that all the sides, all the angles of a square are right angles, therefore angle ADC is a right angle, it equals to 90 degrees. We will define the touching point between tangent DC and this big circle as point G, and we will join together points Q and G by a straight line. Again, QG is the radius of the big circle because of the fact that it exits from the center of the big circle, that is to say point Q, and ends at point G, that is a point on the circle itself, on the big circle itself. Therefore QG is the radius of this big circle, that equals to 2R. And again we have rule number 1. It says that if you have a radius that is drawn to the point of tangency, then the tangent will be perpendicular to that radius. So we have here radius QG that is drawn to the point of tangency, that is to say point G. Therefore the tangent DC is perpendicular to this radius, that is to say this angle is a right angle, it equals to 90 degrees, and this angle is also a right angle that equals to 90 degrees. Okay, so in the next step we will focus on quadrilateral DGEQ. Okay, we will focus on quadrilateral DGEQ. On quadrilateral DGEQ, we will repeat on the same process as we did in quadrilateral PNMB. So in quadrilateral DGEQ, we have 3 right angles, 1, 2, 3, and the sum of those 3 right angles is 270 degrees. And we know that the sum of the angles in any quadrilateral equals to 360 degrees. So actually the sum of these 3 angles, that is 270 degrees, plus the size of this angle that we will define as angle Z, must be equal to 360 degrees according to the rule that I mentioned. Again, 270 degrees plus the size of angle Z must be equal to 360 degrees according to the rule that I mentioned. We'll subtract from this equality 270 degrees, and we will get that angle Z equals to 90 degrees, because 360 degrees minus 270 degrees is 90 degrees, so the size of angle Z is 90 degrees. It is a right angle. Okay, so this angle Z is a right angle, it equals to 90 degrees. So actually in quadrilateral DGEQ, we have 4 right angles, and any quadrilateral that has 4 right angles is at least a rectangle. So I will write down that quadrilateral DGEQ is at least a rectangle. Quadrilateral DGQ is at least a rectangle because it has 4 right angles. And again, we have the rule that the opposite sides of a rectangle are equal to each other. Again, the opposite sides of a rectangle are equal to each other, so the opposite sides of a rectangle DGEQ, they are equal to each other, so that is to say EQ equals to DG, EQ equals to DG, EQ equals to DG, again EQ equals to DG according to the rule that the opposite sides of a rectangle are equal to each other. But we know that EQ equals to 2R. It is the radius of the big circle. So from this equality, we will conclude that DG also equals to 2R. DG equals to 2R. DG equals to 2R. And we also note that according to the rule that the opposite sides of a rectangle are equal to each other, that DE equals to DE equals to GQ, side DE of the rectangle equals to side GQ. Okay, but we know that GQ equals to R, it is the radius of the big circle. Okay, so from this equality we will conclude that GE also equals to 2R, right? DE also equals to 2R. DE equals to 2R. So actually we have quadrilateral DGEQ that has 4 right angles and 4 sides that are equal to each other, therefore it is not a rectangle but a square. So quadrilateral DGEQ is a square. So in the next step we will calculate the value of AE, of line segment AE. Actually AE, as you can see from the drawing, AE, this line segment, equals to AD minus DE. Again, AE equals to AD minus DE. AE equals to AD minus DE. So AD equals to 8 units because it is one of the square ABCD sides, therefore it equals to 8 units. So AD equals to 8 units and DE equals to 2R. So in total we got that AE equals to 8 minus 2R. AE equals to 8 minus 2R. Okay, AE equals to 8 minus 2R. So we know that all the angles of a square are right angles, they are equal to 90 degrees, therefore angle BAD, this angle BAD is a right angle that equals to 90 degrees. Angle BAD is a right angle that equals to 90 degrees according to the rule that all the angles of a square are right angles. But we know that angle BAD, this angle consists of 4 angles. So actually also we can write down that angle BAD also equals to 2 alpha plus 2 beta. Okay. Okay. So from this equality we will conclude that 2 alpha plus 2 beta equals to 90 degrees. This will be equation number 1 that states that 2 alpha plus 2 beta equals to 90 degrees. So here we will divide the equation number 1 by 2 and we will get that alpha plus beta equals to 90 degrees over 2 is 45 degrees. So according to equation number 1, alpha plus beta equals to 45 degrees. I will write it again. According to equation number 1, alpha plus beta equals to 45 degrees. Okay, but if alpha plus beta equals to 45 degrees, then tangents alpha plus beta will be equal to tangents 45 degrees. Okay, tangents alpha plus beta equals to tangents 45 degrees. If alpha plus beta equals to 45 degrees, then tangents alpha plus beta equals to tangents 45 degrees. Very simple. So tangents 45 degrees is 1. So we got the equation number 1 that states that tangents alpha plus beta equals to 1. Okay. This is equation number 1. Number 1 that states that tangents alpha plus beta equals to 1. And we have trigonometric identity for the value of tangents alpha plus beta according to the following trigonometric identity. Tangents alpha plus beta equals to tangents alpha plus tangents beta over 1 minus tangents alpha times tangents beta. Okay. So we will use this trigonometric identity and we will substitute tangents alpha plus beta by this expression that equals to tangents alpha plus beta. Okay, so we will get in equation number 1 that instead of tangents alpha plus beta, we will write down this expression that is actually tangents alpha plus tangents beta over 1 minus tangents alpha times tangents beta. All equals to 1. Okay, so we substituted tangents alpha plus beta in equation number 1 here by this expression, and we got this expression. So actually, in the next step, we will calculate the values of tangents alpha and tangents beta, and we will substitute tangents alpha and tangents beta in this equation number 1 by the value that we will found for tangents alpha and tangents beta. Okay? So, from the drawing, we will focus on the right triangle, this right triangle, triangle APM. Okay, so in triangle APM, this right triangle we know that here tangents alpha equals to PM over AM. Okay, tangents alpha equals to PM over AM in triangle APM. Okay, but what is the value of PM? PM equals to R and AM equals to 8 minus R. So we found out that tangents alpha equals to R over 8 minus R. Okay, again, we found that tangents alpha equals to R over 8 minus R. In the same way, we will find out the value of tangents beta. We will focus on this right triangle, triangle AEQ. So in triangle AEQ, in this right triangle, triangle AEQ, tangents beta equals to EQ over AE. Again, in the right triangle, triangle AEQ, tangents beta equals to EQ over AE. But what is the value of EQ? EQ equals to 2R, and the value of AE equals to 8 minus 2R. So in total, we found that tangents beta equals to 2R over 8 minus 2R. Okay, so tangents beta equals to 2R over 8 minus R, and tangents alpha equals to R over 8 minus R. So we will substitute the values of tangents alpha and tangents beta in this equation number 1 by the values that we found here and there for tangents alpha and tangents beta. Okay, so we will get that tangent alpha is actually r over 8 minus r. Tangent beta is plus tangent beta is 2r over 8 minus 2r. All divided by 1 minus tangent alpha is r over 8 minus r times tangent beta is 2r over 8 minus 2r. Okay, so tangent beta is 2r over 8 minus 2r. All equals to 1. So we got this equation number 1 after we substitute the tangent alpha and tangent beta by the values that we found from tangent alpha and tangent beta. So here we will take a common factor for this expression, and also we will take a common factor in the denominator for 1 in this expression. Okay, we will get that the common factor will be in the numerator 8 minus r times 8 minus 2r so 8 minus r times 8 minus 2r is a common factor for the two expressions in the numerator. So here we will multiply r by 8 minus r, 8 minus 2r, and we will multiply 2r by 8 minus r. So those two expressions are equal to each other, and then we will substitute 1 by 8 minus r over 8 minus r, that is 1, and then we will multiply it by 8 minus 2r over 8 minus 2r, that is also 1, and 1 times 1 is 1, so we change nothing, and then we also have a common factor with 2r. It is actually okay. Here we have it is actually minus 2r squared and all equals to 1. So here we will open the brackets. First of all, we will those expression and this expression are equal to each other, so we can cancel them because one is in the numerator and the other one in the numerator. So we get r times 8, 8r. So we cancelled those two expressions that are equal to each other. One is the numerator and the other one is the denominator is in the denominator, so one is cancelled by the other. So what is left after we cancelled those two expressions is 8r minus 16r plus 16r here we have 8r minus 2r squared plus 16r minus 2r squared all divided by 64 minus 16r minus 8r plus 2r squared minus 2r squared all equals to 1. So that is what we got after we cancelled the two expressions. So it is actually 8r plus 16r is 24r minus 4r squared over 64 minus 16r minus 8r is minus 24r. Here we have 2r squared minus 2r squared is 0, so those two expressions will get cancelled. So we left only with those two, with these expressions. We will cross multiply this expression, equation number 1, and we will get that 24r minus 4r squared equals to 64 minus 24r. Okay. Here we will subtract 24r from this equality and we will get from equation number 1 and we will get that minus 4r squared equals to minus 48 squared minus 48r plus 64. We will add to this equality 4r squared and we will get that 4r squared 48r plus 64 equals to 0. We will divide this equality by 4. This is quadratic equation. We will divide it by 4 and we will get that r squared minus 12r plus 16 equals to 0. So we got this quadratic equation. The general formula for a quadratic equation is ax squared plus bx plus c equals to 0 when a, b and c are the coefficients of this quadratic equation and x is the variable that we are looking for, and we will find out the value of x according to a special formula. The special formula is x equals to minus b plus minus root of p squared minus 4 times ac over 2a and in our specific quadratic equation the variable is r, so x equals to r. The coefficients a, b and c are as follows: a equals to 1, b equals to minus 12 and c equals to 16. So we will use this formula in order to find out the value of r, the value of the values of r. X equals to r, so r equals to minus b, b equals to minus 12, so minus 12 is 12, plus minus root of b squared, b equals to minus 12, so b squared is minus 12 squared, that is 144, minus 4 ac, minus 4 times a is 1, so minus 4 times 1 is minus 4, minus 4 times c is 16, so minus 4 times 16 is minus 64, over 2a, a is 1, so 2 times 1 is 2, and so the values equals to 12 plus minus 144 minus 64 is 80, so it is actually root of 80, square root of 80 over 2. So we have this expression here. 80 equals to 4 times 20, so I write it down. R equals to 12 plus minus 4 times 20 over 2. The root of 4 is 2, so I write it down. R equals to 12 plus minus 2. Inside the root we have only left 20 over 2. So R equals to 12 over 2 is 6, and 2 over 2 is 1, and 20 equals to 4 times 5, so I write it down. And the root of 4 is 2, so we get that R equals to 6 plus minus the root of 4 is 2 times root 5. So we actually have 2 roots for R, so R either equals to 6 plus 2 times root 5, and the second root of R is R equals to 6 minus 2 times root 5, but we know that the size of one side of a square is 8 units, and we know that both circles are inside the square. So the radius of the small circle must be less than the size of one side of square ABCD. So it must be less than 8 units. But here we have R equals to R that equals to 6 plus 2 times root 5 is greater than 8, and R must be less than 8 units, therefore this possibility is incorrect, and we left only with the second solution, that R equals to 6 minus 2 times root 5 units, or it equals to 1.53 units. So I will repeat again. The radius of this small circle equals to either 6 minus 2 times root 5 units, or it equals to 1.53 units. Okay, so that is the answer to the question. Now I'll summarize the lecture. So actually we wanted to find out the radius of the small circle we have a square, one side of a square, the size of one side of the square is 8 units, and the radius of the big square is 2R, and the radius of the small circle is R, and we want to find out the value of R, the value of the radius of the small circle, or the value of R. Okay, so before we solve the question, I presented to you 2 new rules. The first rule is that a tangent to a circle is perpendicular to the radius drawn to the point of tangency. Again, a tangent to a circle is perpendicular to the radius drawn to the point of tangency. So what is the meaning of rule number 1? The meaning of rule number 1 is that if you have tangent AB that is tangent to this circle at point M, that is to say point M is the point of tangency, and you have radius, this radius that is drawn to the point of tangency, then according to rule number 1, this tangent AB is perpendicular to this radius. That is to say, this angle is 90 degrees and this angle is 90 degrees. So whenever you have radius that is drawn to the point of tangency, then the tangent is perpendicular to this radius. This is rule number 1, and we have also rule number 2. Rule number 2 states that if from one external point two tangents are drawn to a circle, then they have equal lengths. So what is the meaning of rule number 2? Rule number 2 states that if from one external point, that is to say from point P, that is external point, we draw two tangents to this circle, tangent PA and tangent PB, then the lengths of those two tangents are equal to each other. That is to say, PA equals to PB. Okay? So, whenever we draw from external point to a circle two tangents to that circle, then the lengths of those two tangents will be equal to each other. That is to say, PA equals to PB. That is rule number 2. Then we actually proved that those two circles can go into each other, therefore those two angles are equal to each other, and this angle, if this angle is alpha, this angle is also alpha. And we proved that those two right angles can go into each other, therefore those angles are equal to each other. So if this angle is beta, then this angle is also beta. And we found out the values of tangents alpha and tangents beta according to the drawing. Tangents alpha equals to r over 8 minus r, and tangents beta equals to 2r over 8 to 2r over 8 minus 2r. And we know that all the angles of a square are right angles, so this angle that is one of the angles of square ABCD is a right angle. It equals to 90 degrees, but this angle consists of 4 angles, so we can write down that 2 alpha plus 2 beta equals to 90 degrees. We will divide the equality by 2, and we will get that alpha plus beta equals to 90 degrees. If alpha plus beta equals to 90 degrees, then tangents alpha plus beta equals to 45 degrees, equals to tangents 45 degrees. And tangents alpha plus beta equals to 45 degrees. We have this trigonometric identity. We substitute the tangents alpha plus beta by this trigonometric identity. So we have this trigonometric identity. We substitute the tangents alpha and tangents beta by the values that we found out for tangents alpha and tangents beta. So we have this equation number 1. We solve this equation number 1, and we got two answers. The first answer is that the radius of the small circle equals to 6 plus 2 times root 5. But because of the fact that it is bigger than the side of the square, it is not correct, because the small circle is inside the square, so the radius must be less than 8 units. So the only answer that is left is that the radius of the small circle equals to 6 minus 2 times root 5 units, or 1.53 units. So the radius of this circle equals to either 6 minus 2 times root 5 units, or in terms of numbers, the radius of this circle equals to 1.53 units. Okay? Thank you very much.